Dr. Groysman is a clinical neurologist here at UCI. He has run a number of clinical trials. In fact, if you're here because you're interested in clinical trials for stroke, there's some information that's at the back of the room. I'm also delighted to announce tonight, I think for the first time, that he has become our assistant director for the Alpha Stem Cell Clinic here. And he's also our director for clinical stroke trials at the Alpha Stem Cell Clinic. So, Lenny.
Thank you. So today we will be talking about the stroke and stem cell therapy for the ischemic stroke. And essentially, that is a mandatory page about the disclosures. And as you can see, I am biased. I am biased about the trials we are doing at the Stem Cell Center. And that's why this page is here. And essentially, I would like to tell you how I got here. And it's not my car, and it's not the new model Tesla Y. Essentially, but I just want to essentially disclose how I arrived here at research in medicine. And essentially, when I was a kid, everything in media, like newspapers, radio, they were talking about transplantations, a new reattached finger, a new heart, kidney saved. And essentially, we live in the industrial world, and it was so easy to understand that we all can essentially use as spare parts, exchange them. And I definitely felt at that time that one day I will transplant something. But unfortunately, when I was still a kid, my grandfather had a stroke. And if I say that at that time, I suddenly realized the importance of neuroscience and that I will be saving people with stroke, it will be probably wrong. Actually, I was really scared. I was scared by the fact how much my grandfather changed after the stroke. And I remember coming out of school and seeing the lizards in the bushes, and I always was thinking about their greatest unfairness, why they can essentially regrow something that they lost and we cannot. And essentially, before I go any further, I would like to talk about the different types of stroke. So on the right, you can see the hemorrhagic stroke. And hemorrhagic stroke means that the vessel in the brain essentially burst, and the blood rushing out of the vessel is destroying the brain. Another type of the stroke is ischemic stroke. As you can see here, there is a blockage in the vessel, and a certain part of the brain is not getting the blood flow. What it means? It means that the brain will die in that area, and the person will lose function associated with that. And it's not my grandfather's, no disclosures here. But as you can see here, the person, our former president, Bill Clinton, is playing golf. And unfortunately, that's not what happens to stroke patients. After people subjected to stroke, victims of stroke, they look quite different. They don't recognize themselves in the mirror, because now the face looks different. Their speech looks different. After the stroke, they have funny movements with their hands, and they're not able to walk. So, but most on top of all that, people lose social connections because it takes too long for them to get to the point. It takes too long to understand them, and they have much lower self-esteem because what happened to them. So essentially, if the people do not recover from time when the stroke occurred to approximately 6 months, the hope for recovery is probably getting less and less. Essentially, almost nobody will recover after 6 months. And if patients kind of can be quantified on this scale, which is a modified ranking score scale, that shows you that the worst case scenario is essentially 6 when the people die from stroke, and 0 is when there is no residual deficits. You can see that people can end up anywhere here. So let's examine what would be the natural stroke recovery. So we would consider modified ranking score 1 and 2 as a good grade, because people essentially can function on their own. They can essentially do their regular activities, though they face moderate deficits. People with MRS, modified ranking score 3 or above, will not be able probably to return to work. So let's see how many people will get over the course of like 1 or 2 years to the normal range. And the results here, as you can see in this article, are not that great. People do recover early on, but then the recovery essentially slows down after 6 months. And some of them will never reach, as you can see in the most severe stroke, they will never reach their potential. So essentially, that's why the idea of the restorative medicine, it's kind of reinventing what nature did for lizards. We may be able to regrow something that was lost. If you need a new muscle, you take muscle stem cells and you transplant that. Hopefully, at some point, we will be able to transplant neurons. Fat cells, anyone? So essentially, the approach to brain restoration is quite simple. We take the stem cells, we essentially modify them sometimes, and we will essentially expand them in the Petri dish. And then these cells can make all the way back to the brain. Hopefully, the brain will regrow and will acquire the function that was lost. And hopefully, at some point, it will be a happy ending. So essentially, there are different types of cells. Some of them are called autologous. Essentially, that are the cells that we are taking from the same patients that will get them later on. And some cells may be allogeneic. The advantages of the autologous cells is essentially that there is no new disease introduced with these cells. There is no possibility of immune reaction to those cells. But unfortunately, sometimes when the patients really, really need these cells, then may not be available, or you don't have time to expand them. So that's why the idea of transplanting stem cells from other donors essentially is so appealing, because these cells can be stored on the shelf and be used whenever they're necessary. And there are different types of stem cells. There are neural stem cells and non-neural stem cells, and there are different mechanisms of the delivery of these cells. You can deliver them intravenously, and with the hope that eventually these cells end up in the organ of interest. You can, of course, when it comes to the brain diseases, you can do it closer to the brain. You can do intrathecal or even intracerebral delivery of the cells. But essentially, when we come to this, the first and most important principle in medicine is called noli nocere. It's essentially do not harm. And as you can see here, the young cell over here is consulting a more experienced, the veteran of the stem cells. And essentially, the cells is saying, I'm so confused. And the reason is that we had bad experiences in the past when the stem cells grew up in something we did not expect. So it's essentially, before we go directly to the clinical trials, there is a lengthy process of evaluating these cells and making sure that they are safe. And safety is probably the most important part of it. You can just take a cell, expand it in the Petri dish, but sometimes you probably, as a lot of us parents in this room, we are quite demanding. We don't want our younger one essentially repeat our path, but probably reach a step or two higher. And that's what this conversation between these two stem cells about. But essentially, you can modify these stem cells, like in an example with SB623 cells, where the cells received an additional plasmid, and essentially look what it caused. So now these stem cells secrete more factors. As you can see, most of these arrows going up. They also promote the neuronal stem cell growth in a much higher proportion. And exactly these stem cells essentially will show a better neuropoietic activity. But on top of that, while the neurons grow, there is probably a significant demand for the nutrients. And essentially, if the vasculature will grow, if you have a more robust vasculature growth, then you will get a faster brain recovery. So as you can see here, the growth of the vasculature with the control stem cells was not as robust as with the cells that were specifically modified. So But it's all good when it grows in the petri dish. How about the animal studies? And it's as close as it gets. Sometimes we do a lot of experimentation in the rat and mice models. As you can see in this rat model, there was a better behavioral, essentially, performance on multiple scales in these stem cells. So, but we know a lot how to improve life of mice and rats, and it's not always works in humans, and that's why there is kind of a decreasing number of drugs that were delivered from the lab all the way to the humans, because we are different. So essentially, once this quite robust research was done, what was done is essentially this the same cells that I started talking about as B623 were used in the clinical trials. And it's a phenomenal clinical trial because essentially, as I show later, there were some real patients that showed signs of improvement. But essentially, these cells were injected directly into the brain. You can see here a frame that allows neurosurgeon to inject the cells into the brain, into the area of interest, meaning that the area that was damaged by the stroke eventually will get the cells, and hopefully it will lead to the new neurons formation. This trial got published in one of the best journals, clinical journals for stroke. And essentially, the data that they presented is quite interesting. First of all, there were no adverse effect from these stem cells. And once again, I keep saying, because in the past we had bad experiences, but now we became much smarter. We look at adverse effect as much as the effects that we can, positive effect that we can create. And as you can see here, there were no adverse effect related to the stem cells, but there were some side effects from the procedure itself when the stem cells were delivered. And what is interesting, this shows the brain and the areas that the cells were injected, approximately over here. And it's interesting that if you do the serial MRIs, essentially by day 7, you will see some activity in the brain that shows that the brain is kind of restructuring itself. And only the patient who had this response in the brain on the MRI eventually became better. What is even more interesting is that by day 28, everything resolved back to original appearance on the MRI. So essentially, all this is, I apologize. All this, not only on MRI, what we want to make sure is that there people not only getting better pictures, but they also improve their level of functioning. And as you can see here on multiple scales, and despite the different directions, they all show improvement. Somehow European and American scales always pointed the opposite directions. So whatever on European is up, the same thing on the NIH stroke scale is down. And as you can see here, on multiple scales, people did improve. But I can bore you with all these graphs and everything, including this one, when essentially the researchers showed that what it shows here is the ability to move different muscle groups and multiple joints. That's what this Fugger-Meyer motor scale shows. And it's not the absolute numbers, it just shows the proportion of people that improved. And, oops. And on top, there is a proportion, it shows the proportion of people who improve significantly. As the time goes, these bars are getting larger. These people had like a moderate improvement. And even though at the beginning some people did get worse, at the end of the trial, essentially almost everyone improved and at least got to the baseline point. So the point of this is that the majority of people improved, or there were no significant side effects. And here, it's exactly where, what was interesting for me is that exactly this trial that I was just talking about, and as you can see here, this person had a stroke.
This is Sonia's stroke. It partially damaged her brain. This is Sonia's stroke. It partially paralyzed Sonia on her right side, and she could barely speak. Her speech was not very understandable. She couldn't order food or communicate well. 2 years later, Sonia could still hardly lift her arm.
So essentially, it's as close to the miracle as it gets, because essentially, as you can see here, the person was able to move it the next day. So, and there are some more examples, and you can find it on YouTube, but it's exactly from that clinical trials. But we participated with the same cells. There was a second phase that we just finished. There are there is no published data. The company is still working on the data, but we saw some improvement in the patients, and hopefully these cells will get approval in Japan. They have a more streamlined kind of ability to put the stem cell and make it available to the public. We expect the phase 3 trial in the United States where the results will be more definitive. Right now we are working on another trial. As I said, the previous trial that I just showed was just finished, and we are starting the new Pisces trial. It had previous 2 phases, Pisces phase 1 and phase 2. They were done in England. It's a different type of cells. This is the name of the cells, CTX-DP, and these cells were essentially immortalized, meaning that they can be multiplied in the petri dish, but once they transplanted into the human brain, they differentiate in the neuronal tissue, and there is no possibility for them to multiply further. And essentially, this trial was initially done in men only. I don't know why they decided to do experiments on men only, but that's what happened. And essentially, they were looking for the patients who had only arm deficits, but eventually what happens, they delivered a different number of cells in the brain. There were no adverse effect related to the stem cells itself, but essentially, eventually they showed that there was even unexpected improvement in some movements. So essentially, as I started at the beginning, the trial was designed to show the improvement only in the arm ability to move the arm, but surprisingly, at least 10 out of 11 patients who had deficits in their leg movements also showed some improvement. And right now, there is a Pisces 3 trial. You can find a brochure like at the back of the room, and we are actively enrolling. We will not be enrolling it like through our stem cell center. There is a centralized number that you can find on this website, pisces3.org. And if you have anyone and you know anyone with a stroke, you can essentially suggest them to go through this website, and people may be eventually directed here. And the endpoint is the ranking score improvement in 6 months. And secondary endpoints would be the multiple scales. So all these 2 trials were for the people who were having stroke in essentially at least 6 months. With a 6 months delay, they would receive their research intervention. But this master's trial that we are trying to bring to UCI, essentially, this is a trial that will be done acutely during the first 24 or 36 hours. The stem cells will be delivered intravenously with the hope to improve the later outcome. And essentially, it's not available here. It's just rolling out around the United States, and there is some promising data from before. They showed that the earlier the cells administered, the better will be the outcome. And essentially, we hope that in the next months or so, we will receive the response from the company, and we will be able to afford to provide these stem cells to our patients. Okay, that's all what I wanted to say.
Next is going to be Dr. Lisa Flanagan. Lisa is an associate professor of neurology, one of our faculty in the Stem Cell Center here, and is on the other side of this game, on the basic science side in animal models. Lisa.
Great. Thank you so much for the introduction. And thank you all for coming tonight. I appreciate you taking time out of your Tuesday evening to come and hear us talk about how excited we are to use stem cells to potentially treat stroke. And so my colleague, Dr. Groysman, did a really nice job explaining what happens with a stroke and some of the problems. And as Dr. Anderson mentioned, I'm now going to go back a little bit and tell you some of the things that we're thinking about in the lab to try to improve the use of some of these cells to treat things like stroke. And so stroke, we've talked about this a little bit, but it's really a big problem, right? It's a big public health concern. It's a leading cause of death, a leading cause of disability, and there are many, many people, many of you in this audience may know somebody, a family member, a friend who's been affected by stroke. And so, one thing that I like to do when I talk about this is make sure that the people in the audience know, what's so crucial about stroke. The one critical thing is that if you're going to get treated for stroke, you have to get treated really, really quickly. All right. So you know what that means? You have to say, well, I feel a little strange. Something's strange with my face. My speech is a little slurred. I'm having a hard time raising my arm. What should I do? Well, maybe I'll go take a nap. No, don't go take a nap. Realize that you're having warning signs of a stroke. Call 911. Go to a certified stroke center like we have here at UCI and get checked out really quickly, because the key thing to remember with stroke is fast. So face, arm, speech, the T is for time, all right? If you're not treated within a really rapid time frame after the onset of stroke, you don't get treated unless you're in one of these clinical trials for stroke that Dr. Groysman talked about, okay? So it's a really crucial thing, and I think this is part of why we're so excited about the possibility of using stem cells to treat stroke, because it's a treatment that can be applied at these longer time scales. So people who didn't get treated early on and have a disability, there's some chance that they'll be able to recover function. Okay. So I think the other reason that a lot of us are thinking about stroke these days is because of the untimely passing of Luke Perry. So a very popular actor, whether you knew him from his earlier work in Beverly Hills 90210 or later his role in Riverdale, this is somebody who was 52 years old, very active in the prime of their life, and literally just dropped dead from a stroke. So it's just kind of reminds us about the critical nature of this and how it's important to find treatments. So why is it? So Dr. Groysman showed the really nice graphic about how people will recover at the beginning and then they really level off. You don't get a lot of additional recovery over time with stroke. So why is that? And so a lot of that is because the brain doesn't really repair itself very well, right? We talked earlier about stem cells in your skin. If you get damage to your skin, it regrows, right? The brain doesn't. And part of that is because the cell types that make up the brain, so for example, the neurons, they don't divide, okay? So if they go away, their little friendly neurons that are left behind are not going to be able to make more neurons to replace them. So what happens then is, in stroke, is you get this really large damaged area. And you have some stem cells in your brain, okay? You have, and we're going to talk about these a little bit more, you have some neural stem cells in your brain, and they get partially activated, but not enough to go in and rebuild this tissue. So the thought is, if we can transplant in stem cells, we can potentially induce repair that isn't happening as part of the normal process. Okay, so there are a lot of different stem cells, and you heard Dr. Groysman talk about the first clinical trial that he talked about was with a mesenchymal stem cell population. Those come from the bone marrow predominantly, and he talked about one that had been modified. And then he also talked a little bit about neural stem cells, and I'm going to talk even more about neural stem cells. Okay, so what are these cells, and where do they come from? So neural stem cells are, I think, really amazing because I think they're the most exciting stem cell type, so I'm a little bit biased. But what's so cool about them is they start out during development as just a single layer of cells. And then they go on to form this complex structure of your brain and spinal cord that lets you do all these things, right? Walking, talking, thinking, dreaming, all of that happens because you started out with just this single layer of neural stem cells. So if you look at your developing brain and you think about where these cells come from, they start out, there are these regions in your brain that are these fluid-filled areas that are called ventricles. Okay, that's what you see here. And along this ventricle, there's an area here where there are cells that are developing, and those are your neural stem cells. Okay? These cells go on to make progenitors that are more committed to turning into a particular type of mature cell, and then they form the mature cells of your central nervous system, so the astrocytes, oligodendrocytes, and neurons. And then, as I said, they go through that process and form this incredibly complex structure of your brain and spinal cord. So what do they look like? So again, I told you I'm biased, but I think they're gorgeous. So this is a red neuron in a sea of green, undifferentiated neural stem cells. And then I'm going to show you again in red, but this time these are astrocytes that have differentiated from this ball of neural stem cells and are now crawling out. So they're really kind of amazing. And so what my lab has really been focusing on is how do we improve the use of these cells for therapeutics for the brain and spinal cord? So how do we optimize them for neural repair? And there's two main areas that we're focusing on. And one is to try to improve the survival and integration of these cells. Dr. Groysman talked about how there's different ways that you can transplant in stem cells. You might put them into, put them in IV or put them into those ventricles that we talked about, but in some cases you might want to transplant them directly into the brain tissue. And what we see with the brain tissue is it's a mess, right? You've had a stroke, so there's a lot of damage there. This is really a toxic swamp of inflammatory cells and dead tissue and dying neurons, and so now we want to transplant new stem cells in there. It's really hard to do. It's hard to get them to survive that. So that's one area that we're really interested in working on. And then the other area is, okay, when we grow up our neural stem cells, it's kind of a mixture of different cell types, okay? And so then they're going to turn into these different types of final differentiated cells. And so that brings up a little bit of a challenge because when we're growing these cells in culture, we don't really have very good ways of determining what kinds of cells are in there and what they're going to turn into. So what that means for transplantation is that, you know, Mrs. Jones might get a transplant today, and the cells that she's getting, well, it turns out most of those are going to turn into astrocytes, all right? Well, Mr. Smith, he gets his transplant two months from now, and his cells, most of those turned into neurons. So how do we compare those? How do we say that, you know, Mrs. Jones and Mr. Smith got the same cells? Well, they kind of did because they were all stem cells, but some of them were going to turn into one cell type, the others were going to turn into another cell type. So it can be very hard to compare. So how do we ask these questions, or how do we start to address some of these problems? Well, many of us are trained as biologists, and when you're trained as a biologist, you have your biology toolbox. You know, there's certain things that we all do. We plate things into 96-well plates. We run, you know, PCR. There's certain techniques that we do over and over again to try to understand what's going on with biology, and that's great, but there's a lot of other toolboxes out there. There's a lot of different fields that we can bring into the study of biology and maybe use them to answer questions in a different way. And so my lab has done this quite a bit, and we tend to do things at the interface of biology and engineering. So what does an approach like that look like to solve some of these problems? Well, if we want to improve the survival and the integration of those transplanted cells, one thing that we can do is create materials that serve as scaffolds for the stem cell transplants. So these yellow lines here are fibers of a material that we can put in with cells that can help to try to improve their survival and integration. All right, how about for the other problem? Well, we'd like to figure out what's going on with these different cell types in the transplants, and one thing that we'd like to do is separate them. So we've been working on new ways of separating these cells so that we can get more pure populations to analyze these cells and transplant them and see how they contribute to neural repair, so that hopefully we can have transplants that are more similar between people and between groups. All right, so what would a scaffold do? So quite a number of things to support these cells. So one is it just can give a physical structure, right? So you saw that picture of the stroke-injured brain, and there's kind of a big gaping hole, and so there's not a lot of structure to the tissue. So one thing that a scaffold can provide is structure to help the cells integrate. It also provides binding sites so that you can see these red cells are sort of attached to this meshwork. You can cross-link in a variety of nutrients and things that we call growth factors that can help the cells to survive, and they can also reduce the inflammation that's ongoing in the damaged brain. So my lab's been working on scaffolds for a while, and we've been using scaffolds that can polymerize in the brain tissue, and we've created these new combination scaffolds. I'm not going to go through a lot of details there, but you can see here's a neural stem cell that's formed a nice differentiated neuron in the scaffold material. And when we've used these scaffold in spinal cord injury, we can see improvement in the walking behavior, which is good to see. We've started to do experiments now where we're using these scaffolds in stroke, and what we're finding is that we see survival of the cells. So these are some green cells that you can see transplanted in the tissue that were transplanted with a scaffold. And in some of our very early studies, so not a lot of repeats, but in some of our early studies, we see that if we include a scaffold with neural stem cell transplants, that we can get a better performance in behavioral recovery afterwards. The other thing that we're finding is that the presence of the scaffold with the transplanted neural stem cells helps to improve the neurons of the brain. So the host neurons of the brain, we see better recovery of those when we have the scaffold. So our data suggests that including a scaffold with those stem cells can improve their transplantation. All right, so what about this other issue that I mentioned, where we'd like to know more about the different types of cells that are being transplanted in and have more control over that process? So how do we do this normally as biologists? So how do we get one cell type away from the other? Well, usually we try to use markers. So we'll say, okay, so this cell that's going to turn into an astrocyte expresses a certain set of markers that's different from this cell that's going to turn into a neuron. But what's been really challenging in the neural stem cell field is that we don't have a lot of those markers. And so we decided to take an approach that was really different, and we're doing a way of sorting the cells where we're using electric fields, which sounds really bizarre to a lot of our biology colleagues, but it's really kind of a cool technique because you can put a cell in a particular type of electric field and you can induce movement of the cell that doesn't need any markers or labels. It's just moving based on what kind of cell it is, all right? And so I'm going to show you a little bit about what that can look like. So this is one of our devices, and so these are very small devices that are fabricated, and you can see that we have electrodes here in gold. And in this particular experiment, we've pseudo-colored our cells. So right now, we've set up the electric field in a certain way. So we have both our green cells and our gray cells that are attracted along these electrodes. So we've trapped them, right? So then what we can do is we can change the electric field. We change the frequency of the applied electric field, and we can release the gray cells and leave behind the green cells. Then we can change the frequency again and release the green cells. So using that type of approach, we can separate those two cell types from each other. And when we do this, we find out that when we use electric fields that are high frequency, we tend to pull out cells that turn into neurons. And when we use electric fields that are low frequency, we pull out cells that turn into astrocytes. So that gives us a way to start to isolate these cells from each other without having to use labels. So, I hope that I've convinced you that by taking a little bit of a different approach, and in our case, we combined biology with engineering, we're able to find out new things about stem cells and hopefully improve their use as therapeutics so that as we continue to move forward with clinical trials like Dr. Groysman talked about, we can just continue to have cells be more and more effective at improving repair after neural injury like a stroke. So these are the folks who have done a lot of the work in my lab. This is my contact information. We're going to take questions, all three of us, but if there's anything that comes up that you didn't get a chance to ask, feel free to shoot me an email or check out our website. Thank you.
So let's see, can you grab that microphone? So floor is open for questions. Anything you guys would like to ask, I'll try and dash around with a microphone. If I don't get to you, please speak loudly, and you guys remember to repeat the question, please. I'm sorry? No.
So,
Yes, you have to face that direction.
oh, so this may be a dumb question, but I heard that electric field only like moves charges. So do we need to charge the stem cell if we want to move it with the electric field? It's like a bunch of negative stem cells.
Okay, so that's a good question. And so it depends a lot on the type of electric field that you set up. And there is thought to be a redistribution of charges that occurs in this type of electric field. I can tell you a little bit more about it in detail after. Basically, we're using something called dielectrophoresis, and so you set up a non-homogeneous electric field, and what happens is as you change the frequency, you induce a polarization, and that's where the charge kind of comes into it. And that induced polarization creates a force for movement that can then pull cells either towards the high-strength part of the electric field or away from that to the low-strength part of the electric field.
Yeah?
Hi. Regarding the electric field also, there is no any side effect or to damage this kind of cells and so on, or no?
That's a great question. And so when we started this work, there were people that had worked with these types of electric fields before, but nobody had done much with stem cells and certainly not with neural stem cells. So one of our early set of studies that we did, I had a graduate student who was really focused on this, and he said, okay, if I'm gonna put cells into these electric fields, first of all, do they die, right? Second of all, if they don't die, does anything change about how permeable their membrane is? Does anything change about how well they divide? How about what they differentiate into? And so he did a whole series of studies. And what he found is that basically they're fine, okay? Most of the frequencies, most of the amounts of exposure time, they were fine. We did find that there's a certain frequency range that we can use where we do kill off some of the cells, like about 10% of the cells, but not all the cells. So that was really good to know, because now as we design all our experiments, we avoid that. We just don't expose them kind of in that frequency range for the amount of time that causes cell death. And so as long as we avoid that, we don't change anything else about their proliferation or differentiation or anything else. Good question.
Hi, so I was wondering, you talked about how different charges make different types of cells react differently, right? So what specifically makes like neurons react a certain way under a certain charge, and what makes other cells react a different way?
So that's a good question. So we had to try to figure out, so then, it brings you back to the biology, right? Okay, so we're using these engineering electric fields and we're inducing cell movement. And why? Why is one cell type moving in a certain direction and the other cell type isn't? And so we narrowed it down to something about the plasma membrane of the cell. And then we did further studies to see, okay, so what's changed about the plasma membrane? And really what we've found that's the key thing is the sugars that are on the surface of the cell. Okay, so when your cell is doing its normal thing and putting proteins out onto the cell surface, it tends to put a lot of sugar molecules on them. And we're finding that the types of sugar molecules that they're putting onto the proteins that end up on the surface of the cell are different for cells that are going to turn into neurons compared to cells that are going to turn into astrocytes.
Somebody on this side of the room for something different. Come on. Yeah?
Just wondering, is there any frequency that produces oligodendrocytes like the other one you talked about?
Yeah, that's a good question. And so we haven't figured out exactly what's going on with oligodendrocytes yet. And part of that is because the cells that we've been using in our studies don't make a lot of oligodendrocytes. And so it makes it a little bit hard to answer that question. So the only tidbits of data that we have so far is that we might have some cells that we can pull out that will make both neurons and oligodendrocytes, which is a little bit interesting. But it's still a little bit of an open question. So that's a good one. And if anybody wants to come to my lab and figure that out, we'd love to know the answer.
Does anybody have a stroke trial question? Oh.
Hi. It seems like a lot of the research you guys did was on the ischemic stroke. Is the recovery for both the hemorrhagic and the ischemic stroke similar when you inject, say, the SB623 or any sort of modified stem cells into it? Are they similar?
That's a very good question, because essentially hemorrhagic stroke usually causes more destructive lesions, and I guess the researchers were just scared to try. So there are no clinical trials in hemorrhagic stroke, only in ischemic.
I saw some, there we go. Yeah.
Why, I don't quite understand, why is all the funding and granting and everything going to early on patients, and why is it not interesting to have clinical trials and studies of stroke patients that are further out, more than a year out?
Oh, I'm sorry, I probably didn't make it clear because it's a very good question. So essentially, as you pointed out, a lot of recovery happens early on. So the first clinical trials that I talked about with the SB623 cells were directed towards the patients who had stroke 6 months or more. So it's essentially a chronic phase. The newer trials that we are developing right now, they are for the acute phase. But as I said, there will be probably a phase 3 for SB623. So right now we have the full spectrum from people who just presented to the hospital within like 24 hours to people who are approximately 6 months, and SB623 are being tested in people from 6 months essentially to 5-6 years out.
Okay, thank you.
So the multi-stem, that's for like 24 hours to 36 hours. The SB236, that can go out to like 5 years or so. The Pisces, neuron type, that can also go out up to like 60 months. Exactly. So when this pans out, eventually FDA approval and so forth like that, is there going to be differentiated for sure which one's going to be better, the SB236, the Pisces for neuron one? I mean, is there kind of like a competition between the two, or just whichever one seems to work best? Is that what the patient's going to eventually get FDA approved, or how is that going to pan out?
Let's say, first of all, we're still early on. We don't know if all 3 companies will get their stem cells products on their market. The second part is the design is very smart. If you, from the pharmacological standpoint, essentially, they don't compete directly. One is just for the acute stroke, another one for essentially 6 to 12 months, and the SunBio is aiming at a chronic stroke up to 5 years. So they're not directly competing. Second of all, what we see in pharma, they usually don't like head-to-head trials. They just want to show non-inferiority, and what it means that the both products will be available to the patient, and it will be up to the physician, and physician believes which one to suggest more strongly to the patient. Thank you.
I did have a question about the time frame, but I think that got answered by the previous question. Who are you doing the clinical trials for, the early people or the later on? So I think I understand that now. I just would like to make a comment, though, about the time of the urgency to get the stroke patient into the hospital, because this is true and this is good, except there is one exception to that. If your patient is on blood thinner, they will not treat them right away. They don't get whatever the treatment is for the person that gets there within 4 hours or 6 hours, because we went through that. My husband being on blood thinners, and I kept saying, why aren't you doing this special, wonderful treatment that stops the stroke? And they said, we can't do it because he's on blood thinners. Could you address that issue?
Sure, and if you don't mind, I know Dr. Flanagan very appropriately said, first of all, you don't have to go to the hospital, you have to dial 911 and make sure that the emergency vehicle will bring you to the hospital, because essentially the emergency vehicle will choose the right hospital where the treatments are available. And the second part is, it's very important to understand that essentially when you come through the emergency vehicle kind of delivery pathway, the hospital will be alerted in advance, so a neurologist maybe even be waiting for you at the door. Second part, and I'm sorry that it happened to your husband, but essentially when the people on the blood thinners like Coumadin, warfarin, or some newer agents, we don't give only one agent, TPA, but approximately a year ago, American Heart Association had a presentation, and this now approved by FDA, that there is a newer treatment, is a stent retrieval. So despite the fact that we cannot give the blood the clot-busting medication TPA, we now can essentially go with this special device and essentially pull out the clot mechanically up to 24 hours. And it may be done even in people who are on blood thinners. So right now, and it's just the situation changed in the last year, where we are able to essentially help people even who were on anticoagulation and essentially failed this preventive therapy.
Other questions? Yeah.
Hi, I have a question if there have been any clinical trials integrating stem cells with stents for treating aneurysms in the brain. Like if you insert a stent to restrict the blood flow to that area, if they're doing any stem cells with that.
And I will, so essentially in clinical practice there is none. I know that right now there are an attempt, first of all, to understand the dynamics of the aneurysm, and you're right, aneurysm is an aneurysmal bleed is another type of stroke, more rare. There are only 3,000 cases in the United States, while the whole lot of the stroke cases is probably like on the range of 700,000 cases a year. So it's a minor proportion, and unfortunately all the people present already with quite significant damage done from this ruptured vessel, and after that, the brain, if there is an intracerebral hemorrhage from the aneurysm, the recovery will be similar to the other types of hemorrhagic stroke. So the stents that are available right now, we have the ability essentially to cover the aneurysmal site with essentially, it's like a mesh. That's one approach, or you can put the coils inside. It creates a clot inside the aneurysm. So I don't think that there will be studies specifically directed toward this particular type of stroke.
All right. So thank you very much to our speakers. Lenny has a very challenging clinical schedule. Lisa's traveling tomorrow, so a big round of thanks. And thanks to everyone in the audience for joining us tonight. We always welcome you here. Thanks again.